Hello everyone, and welcome to this video on identifying terminology associated with transformations. So this video, I'm not going to be doing a lot of writing. I've already pre-written a lot of pages in which I just go over lots of terminology associated with transformations. I define a transformation, and then the domain of a transformation, the codomain of a transformation, the range, what is the image of an input or the pre-image of an output vector. Just lots of terminology and some examples where I point out proper wording and proper usage of the terminology. Okay. So beginning here with the definition of a transformation. It's basically a more generalized function, if you're familiar with functions, as I'm hoping you are by this point if you're watching this. So a transformation, say t, the name of the transformation t, or the name of the rule, a transformation t from vector space Rn to vector space Rm. Alright, so we're going from Euclidean space to Euclidean space in this video. In a future video, I will talk about just transformations from general vector spaces, say from vector space V to W, and all the terminology will be very similar. We'll be going more general. But for right now, we're going from a Euclidean space Rn to another Euclidean space Rm. The way this transformation is denoted is, the name of the transformation, t, little colon or maybe a bar, and then, from Rn, arrow, Rm, Rn to Rm. Right. Alright, so a transformation t is a rule that assigns an element of the vector space Rn, right, the first set, the left set, to an element of vector space Rm. Right, the right set. So it takes an element from Rn, maps it to or assigns it to an element of Rm. So here's an example. I have a transformation t from, say, R2 to R3. So my inputs are going to be vectors with two components from R2, and my outputs are going to be vectors with three components, right, from R3. And the way the rule is defined is this way. And it's just like function notation, where you have the name of the rule, right, t, the name of the transformation. Then in parentheses you have your input vector or your input element. Maybe I should write that. So in the parentheses here, right, this is our input element. And see how it's from R2, right? It's a vector with two components, x1, x2. And this is equal to, and then over here, a vector from R3, right? It's got three components. Our output vector, right? Description of the output. And you see how each component in the output is made by using the components of the input. Right. So the first component of the output is, I take x1 plus x2. Second component, I take x1 minus x2 from my input. And then the third component, I take x2 squared from my input to create this output vector from R3. So any rule that assigns, an input to an output is a transformation. All right, so this is an example of a transformation from R2 to R3. Wonderful. And looking further at this, we can talk about how this see how this assigns a vector from R2 to a vector from R3. Let's look at one example of that I've written here. Again, this is just one example of an assignment. So if I take my input, vector 1, 2 from R2, apply the rule t to it, right, transformation t of the vector 1, 2 is equal to, and then again, just going through this rule, replacing all the x1s over here with the number 1, and replacing all the x2s over here with the number 2. So the first component of my output, 1 plus 2 is 3. The second component, 1 minus 2 is negative 1. Third component, 2 squared, or 4. Alright, so T is a rule, right? T is a transformation that assigns the vector 1, 2 from R2 to the vector 3, negative 1, 4 from R3. And again, you can think of all sorts of examples here. Just replace this vector here with any vector you wish from R2, maybe 5, 7, 0, 1, 0, 0, whatever you want, and see what vector in R3 that would be assigned to. It's doing a simple plug and replace variables with numbers and simplify. Okay, so again, the whole video is a bunch of definitions. Right, so some more definitions. Right. So the domain of a transformation is the set of all inputs. Right, so where all the inputs are coming from. So in that last example, the domain was R2. Right, all my input vectors came from R2. The codomain, right, codomain of a transformation is the set of all potential outputs. I emphasize potential here because it's that second set that you're being mapped to. So again, in the previous example, my domain was R2. All the inputs were vectors with 2 components. My codomain was R3. Right, the set that was being mapped to. All the outputs had 3 components. Now, the codomain, don't confuse this with the range. Right, the range, as we'll see later, is the set of all the actual outputs. I say the codomain. Now the codomain could be equal to the range, but the codomain is a set of all potential outputs. Right. So just because in the last example, for instance, the codomain was R3, that does not mean that every vector in R3 is mapped to by some input in R2. There might be some values, some vectors in the codomain that aren't mapped to, that aren't being assigned to any input from the domain. All right, so that's why I say the codomain of a transformation is the set of all potential outputs. Right. So in the transformation, T from Rn to Rm, the first set, right, Rn is the domain, the set of inputs. And that second set after the arrow, Rm, is the codomain, the set of potential outputs. And if these two are the same, if both of these are R2 or both of these are R3, the transformation is given a special name. A transformation is called an operator if the domain and codomain are the same. Right. So I've got an example written out on the next page where I use these words: domain, codomain, and operator. Alright, so here's another example of a nice rule, a transformation. Say T from R3 to R. So my inputs are vectors with 3 components. Right, my inputs are vectors from R3, and then my potential, where the outputs are coming from, the codomain is just the real numbers. Now you could say vectors with 1 component, but very often, because just if you have a vector with 1 component, that's really just a number, a real number in this case. So instead of writing little brackets around this, very often when you're dealing with just a set of real numbers, right, R1, vector brackets or parentheses or whatever vector notation you're seeing in the text you're looking at, usually that's not written out. Right. So in this case, the rule, t takes a vector from R3 with, x1, x2, and x3 as components, and maps it to, assigns it to the real number x1 squared plus x2 squared plus x3 squared. Right. So again, no need for a bracket around that. There's only, you can if you want. Right. You can make that a vector with one component, but again, not really any need for that. So in this example, the domain of the transformation is R3. Right, that's where my inputs are coming from. The codomain of T is R, right? The real numbers, where the outputs are coming from. Now, as I mentioned earlier, on the last page, don't confuse this with the range. This is not the range, right? Because if I have x1 squared plus x2 squared plus x3 squared as my output, right, this will never be negative. Right? Remember, when you take any real number and square it, it's non-negative. So my outputs are never going to be negative. So do you see what I'm saying? Is there can be values in the codomain that aren't outputs. Right? The negative numbers in the real numbers, the negative real numbers are not outputs for this transformation. So be careful with that. Don't confuse the codomain with the range. They are not always the same. Okay? They can be, but they're not always, like in this case. All right, so very simple. Domain, first set, codomain, second set. Inputs, outputs. Possible outputs. All right, another example, t from, say, R2 to R2, right? So my inputs come from the set of vectors with two components, and my outputs also come from the set of vectors with two components. And the rule for this is, say, t of x1, x2 equals, and then again, a vector with two components, my input, a vector with two components, my output, where the first component is x1 minus x2, and the second component is 3x1 plus 5x2. This transformation here would be called an operator. Right? This transformation is an operator since the domain and codomain are the same. Right? In this example, they're both R2. Right? Like I said earlier, if they're both R3 or both R4 or both R, you have an operator. Right? Now I might accidentally say the word transformation. They're all transformations, right? Every operator is a transformation, but not every transformation is an operator, right? Like this transformation up here would not be an operator because my domain and codomain aren't the same. Okay. So now for some more definitions, more terminology. All right. So again, all my transformations in general, I'm writing out here from Euclidean space to Euclidean space. So in the transformation T from, say, Rn to Rm, the vector T of x. Now this would be an output, right? Remember, the vector in the parentheses after the name of the transformation is my input, and then the whole thing, T of x, is my output. So the vector T of x, which is in Rm, right, in the codomain, it's one of the outputs. It's a possible output. The vector T of x for a given vector from the domain Rn, right, for a given vector x from the domain Rn, is called the image of x under T. Right, so that may sound weird there. Let me go into an example. So for instance, suppose I have transformation T here from R4 to R2. So my inputs are vectors with 4 components. My outputs are vectors with 2 components. And the rule for it is this. Right, so if I take T of, and then this vector from R4 with components x1, x2, x3, x4, say that's equal to, and then again the output is going to be a vector with two components, something from R2, where the first component is the sum of the first two components here, x1 plus x2, and the second component is x3 minus x4. Alright, so let's take one example. Say this vector here. So suppose my input is, again, from R4, has the components 1, 2, negative 1, and 5. Well, the value of t at this vector would be something from R2, right, where the first component's 1 plus 2, right, x1 plus x2, 1 plus 2, so 3. And the second component, negative 1 minus 5, right, x3 minus x4, negative 1 minus 5, negative 6. So t of 1, 2, 1, negative 1, 5 is the vector 3, negative 6. What I was saying up here with the image, as when it applies to this, would be said the following. So this output vector, right, 3, negative 6, is called the image of the input vector 1, 2, negative 1, 5 under t, right, under the rule t, or the transformation t. So an output vector is an image of some input vector. Right? Basically, when you say a vector is the image of something, that means that this vector is mapped to by this input. Right? So 3, negative 6 is the image of 1, 2, negative 1, 5 under t. I hope that made sense. That's the only one I wrote. Because it's very simply just plugging in values, replacing variables with numbers and getting outputs. And then that output is the image of the input. Okay, now another definition. So again, in transformation t from Rn to R, that's R, sorry, that looks crappy, I drew it poorly. In transformation t from Rn to Rm, the pre-image, right? So the last page was about the image of, the image of an output was its input. Or I'm sorry, the image of an input was its output. My bad. The image of an input is its output. This is the other way around. The pre-image of a vector in the output set, right, in the codomain, a vector v from Rm under t, is the set of all elements, all vectors from the domain Rn, all elements u from Rn, such that t of u equals v. Alright, so image on the previous page, let me bring that back. So let's compare these. The image of an input is its output. Right? The image of an input is its output. The pre-image of an output is all the inputs that map to it. Alright, so the pre-image of some output is all of the inputs that have that output as an image. Alright, if that makes sense from the previous page. So for instance, so this can be a bit confusing. I'm hoping I have a few more examples of this pre-image notion. Alright, so here I have the operator t, right, or it's from R to R, real numbers to real numbers, so again it's an operator. I have the operator t, such that here's the rule t of x. Now you could say x1, but again there's only one component, so that's why I notice I'm not putting it in the vector brackets or anything like that. Again, it's just a real number. T of x equals 3x plus 1, and this is something you're more familiar with from maybe pre-calculus or algebra. In pre-calculus or algebra, or whatever earlier classes you've taken, most of your functions were from real numbers to the real numbers. Inputs were real numbers, outputs were real numbers. So that's what I got here. So let's suppose we take a value from the codomain, right? A possible output. Take 7 from R. That's a real number, and again, this is the codomain R, this set. Take 7 from the codomain. the pre-image of 7 under T is the set of all inputs that would yield an output of 7. Or in other words, all values of the domain, right, all x belonging to R, and this R is the domain R, all values in the domain such that the image of that is 7. Right? All the inputs whose image is 7. Right? So if you take a look at that, what values have an image of 7? So when is the image of x equal to 7? Well, that's when 3x plus 1, right? The image of x is 3x plus 1. And when is that equal to 7? Well, when x equals 2, and that's the only value. Right? That is the only number that I could plug in here and get an output of 7. So they would say that the pre-image of 7 under T is just the set with 2 in it. Right? Because only the number 2 has an image of 7. Only the number 2 can be plugged in to give me an output of 7. Now I'm going to go to, the reason I'm doing this R to R, the operator here, is because I want to show you a picture too. Right? You can again, back in algebra, pre-algebra, when you were looking at functions from real numbers to real numbers, you could picture those on the XY coordinate plane. Right? Where the this is that Desmos website, desmos.com, free online graphing calculator. The x-axis represented the domain real numbers, and the y-axis represents the codomain real numbers. And if I look at the graph of f of x equals, or in this case t of x equals 3x plus 1, remember that looked like this. It was just a line with a slope of 3 and a y-intercept of 1 and all that. And we're asked for what's the pre-image of 7. Right, so I go to 7 on the codomain. Right, the codomain is represented by the y-axis. You go to 7 on the codomain, and look, oh, there's the point. There's the point of this graph that has 7 as an output. And look at that. Look at the input. The input is 2. Right, so that means the pre-image of 7 is only the number 2. Right, only the number 2 has an output of 7 or an image of 7. Right. Okay, so that's what I meant when I wrote this. Right, that the pre-image of 7 under T is the set with only the number 2 in it. Now, I have other examples besides this because I want to point out, the image of an input is going to be a single output. All right, you saw earlier, you saw on this page, the image of some input is a single output. All right, but the pre-image of an output, like the pre-image of 7, might contain more than one value, might be more than just one input, because there may be more than one input that has that particular output as an image. So in this example, the pre-image of 7 has only one value in it, 2. But let me show you other examples. Right? Sometimes the pre-image may have multiple values, more infinitely many values, or no values. Let me show you here. All right, so here's another one, another operator from R to R, so I can show you a picture, on the XY plane, where the x-axis again represents the domain real numbers, and the y-axis represents the codomain real numbers. So I have t from R to R here, such that t of x is x squared, right? So again, my input is a real number, my output is a real number. So no need for the vector brackets here. There's only a single component. Now, the pre-image of 4, right? And again, this 4 is coming from the codomain. The pre-image of 4 under T is this set. The set with -2 and 2 in it. There are 2 values in the pre-image of 4, as opposed to the last example where there was only 1 value in the pre-image of 7. And the reason that the pre-image of 4 under t is negative 2 and 2 is because both of these have an image of 4. Right? The image of negative 2 is 4. The image of 2 is 4. Both of these have an image of 4, or when you plug them in, negative 2 squared or 2 squared, you're getting the output of 4 back. All right, so you're seeing here that the pre-image of an output, the pre-image of some codomain value, isn't going to have always just one value in it. Another example from this same operator, the pre-image of 0. Again, this when you talk about the pre-image of some element, that element is from the codomain. So the pre-image of 0, right, from the codomain under t is just the number 0, right? This is the only value of the domain, right? This value is from the domain, this 0. This is the only value of the domain that has an image of 0, right? T of 0 is 0. 0 has an image of 0. And the pre-image of 0 is just a set with 0 in it, because that's the only one that when I plug it in, I get an output of 0. But that's not all. Sometimes a pre-image can have nothing in it, be the empty set. For instance here, this same operator, the pre-image of the number negative 1. Again, this negative 1 is coming from the codomain. The pre-image of negative 1 under t is empty. Right? You can write it as an empty set of brackets or a circle with a slash through it. The reason is because there is no value in the domain. There's no number in the domain, no x belonging to R, right, the domain R, such that x has an image of negative 1. T of x is negative 1. Right, again, because you're squaring things here, right? This is x squared. You take the image of any real number, t of x, and that's equal to x squared. Any real number squared is never going to be negative. So the pre-image of negative 1 under t is empty. Again, we can visualize this because it's just simply from R to R. I can visualize this again on the coordinate plane. So let's get rid of the 3x plus 1. Here's x squared, right? T of x equals x squared. Now I asked about the pre-image of 4 earlier. So when they say what's the if I said what's the image of 4, you plug 4 in and get 16, right? The image of 4 would be 16. The pre-image of 4 is I go to 4 on the y-axis or on in the codomain and look for inputs that take me to that output. So here's 4 where my cursor's flying around, right? There's 4 on the in the codomain, and you see that there are 2 points of the graph here with an output of 4. So one of them is 2, 4. So one of the values in the pre-image of 4 would be 2, because 2 has an image of 4. And then the other value that would be in the pre-image of 4 is negative 2. Right? You see how negative 2 has an image of 4? So negative 2 is in the pre-image of 4 as well. We talked about 0, right? See how go to 0 on the y-axis? The only value that has an image of 0 is 0. Right? So the pre-image of 0 is just the set with 0 in it. Right? And then you look at negative 1. There are no points of the graph, right? Go left and right here on negative 1 on the y-axis, negative 1 from the codomain. There are no points of this graph that have an output of negative 1. Right? So negative 1 has a pre-image that is empty, right? Nothing in it. No value on the x-axis, no value from the domain has an image of negative 1. So again, I hope that's clear here what I'm saying. Now I do have one more example where I'm not going to really be able to picture it as well. Yeah, so I could picture this in 3 dimensions, but didn't bother pulling that up. All right, so here I have one more example of a pre-image. Now, so far you've seen the pre-image of a value having 1 value in it, or the pre-image having 2 values in it, or no values in it. But the pre-image can have any number of values in it. You could have infinitely many elements in the pre-image. So for instance, say my transformation t here is from R2 to R, so now my inputs are vectors with 2 components, and my outputs are simply a real number. And here's the rule. So t of the vector, x1, x2, my input is a vector from R2, my output is a real number, x1, just the sum of the 2 components, x1 plus x2. The pre-image of 0 under t, right? 0 is from the codomain, right? Under t is the following. Now, what I would be doing here is looking for, maybe I'll do a little writing here. All right, we'd be looking for when is this equal to 0? What vectors have an image of 0? So when is x1 plus x2 equal to 0? Well, that's when x1 equals the opposite of x2. So vectors that look like this, where, again, x1 is just the opposite of x2. And if I pull x2 out of this, right, x2 is just some real number. Do you see how every multiple, and x2 is just a real number? You could call it, I call it t here, right? But t is any real number. So every vector that looks like this, every vector that's just a scalar multiple of the vector -1, 1, has an image of 0. So that means the pre-image of 0 is all these vectors, is the set with all these vectors in it. Every single vector that looks like this has an image of 0, has an output of 0 in this particular transformation. So the pre-image of 0 under this transformation is this. Remember all scalar multiples of a vector is the span of that vector. The span of the vector -1, 1, or all scalar multiples of -1, 1, right? All the vectors that look like this, t times the vector -1, 1, where t is real, right? And that's because if I put, multiply these by t, it had -t here, t there. If I plug that into this function, the vector -t, t, you'd get -t plus t, or 0 all the time, right? So every vector that looks like this has an image of 0, meaning that the pre-image of 0 is every vector that looks like this, right? All scalar multiples of -1, 1, or the span of -1, 1. So infinitely many values, right? -2, 2, 5, -5, 8, -8, 0, 0. All of these vectors belong to the pre-image of 0. Right, lots of stuff. All right, so hopefully pre-image makes some sense now. All right, it's just all the pre-image of an output. The pre-image of a value from the codomain is all the values from the domain that have that output as an image, right? That map to that output. All right. Now for the last major definition when it comes to transformations and operators is the range. Now I mentioned the word range earlier in the video, right? I was telling you not to confuse the codomain of a transformation with the range of that transformation, and here's why. So in transformation, again, just general transformation from Euclidean space to Euclidean space, t from Rn to Rm, the set of all elements of the form t of x, right? So all the outputs that actually get mapped to, where x is some value in the domain, right? X belongs to Rn, is called the range of t. Another way you could write this is the range of t is all vectors that look like this, all vectors that are of whatever t of x looks like, such that X is from the domain, right? So remember how I said earlier, remember the codomain Rm, this was the set of all potential outputs, where all the outputs are coming from. But not every single value in here is an output, right? All the time. The range of T is the set of all actual outputs, right? These are all the values in the codomain that are actually outputs in the transformation that actually get mapped to by the transformation. All right, so I have one example where I just go, again, it's something I can picture on the XY plane, so some transformation or operator from R to R, the reals to the reals. And it's something you're familiar, y equals x squared plus 1, or in this case, t of x equals x squared plus 1. Now I could write the range of this in this way, the way I wrote it up here. The range of t is the set of all numbers that look like this. X squared plus 1, right? What t of x looks like I said here, whatever t of x looks like. The range of t is all the numbers that look like this, x squared plus 1, such that x belongs to the domain, right? Such that x is a real number. Now, if you look at the picture of this on the coordinate plane, right? Go back here. So here was t of x equals x squared plus 1. Remember the range is outputs, right? So the range is made up of values that are from the codomain. And the y-axis, when you're talking xy plane, the y-axis represents the codomain. Well, look, all these values down here, -7, -6, -5, -4, -3, -2, -1, 0, all these values down here in the codomain are not mapped to. They all have empty pre-images, if you think about it that way, with pre-image. Or no domain value maps to these, all the way up to +1 here. And then starting at 1, right, there's 0, 1. See how 1 is the image of 0? Right? Starting at 1 and going upward, 2 has a non-empty pre-image. 3 has a non-empty pre-image, right? 4 has a non-empty pre-image, and so on. All the values from 1 and up, 1 and greater, have a non-empty pre-image, right? There are values that actually map to them. So we could also describe the range this way, right? This second way here is all the value. Now I called it y just to not confuse it with x. The range of t is all values in the reals, all the values in the codomain. Right? Again, this R here is the codomain. All the values from the codomain such that those values are greater than or equal to 1. So notice again, that is not the entire codomain. That's not all of R, but only the values greater than or equal to 1. So what we're seeing from this example is that and this is huge, I put a little bubble down here, and I write it again on the next page even. The range of t, the range of a transformation, is a subset, right? That's what this little sideways U with the little half equal sign under here. The range of t is a subset of the codomain of t. Right, I'll write that in here. Again, what this symbol means, this is a subset of meaning that every value in the range is in the codomain, but not necessarily the other way around. Now they may be equal, right? That's why the little or equal to is under here. But if they're not, you can not write that and just say it's a proper set. Like in this case here, in this particular example I've written here, the range of t is a proper subset of the codomain, right? There are values of the codomain that are not in the range, right? Like all the values less than 1. All the values less than 1 are in the codomain, right? They're in the reals, but they're not in the range. So be careful. Don't again, as I said before, do not confuse codomain of a transformation with the range. So the range of a transformation will be a subset, may be equal, but will be a subset of the codomain of the transformation. All right, so here's a case where they're not equal, right, where the range is a proper subset of the codomain. And then I have one other example here where the range is equal to the codomain. Sometimes they are equal. And when they're equal, they call that kind of a transformation an onto or surjective transformation, but we'll get to that in a future video talking about those kinds of definitions. All right, so my last example here, transformation from R3 to R2. So my input vectors are vectors with 3 components. My outputs are going to be vectors with 2 components. And I have it set up here, t of x1, x2, x3, this vector from R3 is equal to this vector with 2 components, where I take 2x1 plus x2 plus x3 for the first component, and then x1 minus x2 minus x3 for the second component. Now the way you could describe the range, especially when there are these linear expressions here, right, all these variables to the first power, and there's no constants, no plus 5 or plus 3. So especially when you have these linear expressions like this, the range can be expressed in a multitude of ways. So I can write it the way I was in the last example, the first way. The range of this transformation is the set of all vectors that look like this, right? Just what t of x looks like, what t of the vector looks like. So all the outputs all the vectors that look like this, such that the input vector comes from the domain, right? x1, x2, x3 comes from the domain R3. So totally valid to write this as the range. It's what the range is, all the outputs. But if you think about this, this is a 2x1 vector here, a 2x1 matrix, 2 rows, 1 column. And again, these are nice and linear. All the variables are to the first power. There's no constants being added, no plus 5 or minus 3. So in that case, right, when you had linear expressions, you could actually split it up into the sum of a bunch of vectors. If I split it up to x1 times, and then the vector with the coefficients of x1. So real number x1 times vector 2, 1 plus real number x2 times vector 1, negative 1, right? Just the coefficients of x2 plus then real number x3 times, and again the coefficients of x3, the vector 1, negative 1, where x1, x2, x3 belong to the reals. You could write this range this way as well, right? And remember what these are. This is just a linear combination of the vectors 2, 1, 1, negative 1, and 1, negative 1. Now I know I don't need to repeat 1, negative 1. We'll see that in a second. But so the range of t is all linear combinations of these 3 vectors. Well, remember, the set of all linear combinations of a set of vectors is the span of that set of vectors. So you could also say that the range of this transformation is the span of 2, 1, 1, negative 1, and 1, negative 1. And I'm hoping that it's clear that you don't need to repeat a vector, because clearly this vector and this vector are not independent of one another, right? So I can get rid of that one, and then these 2 are independent. Remember, a set of 2 vectors is linearly independent if they're not scalar multiples of each other, and these are not scalar multiples of each other. So the only 2 I really need are these 2. So I could say the range of t, the range of this transformation, is the span of vectors 2, 1, and 1, negative 1, right? Or all linear, the set of all linear combinations of these 2 vectors. And this set of these 2 vectors is linearly independent, right? So this would form a basis for the spanning set, for the range. And these are vectors from R2 that have a basis with 2 vectors in it, a dimension of 2. So that means this is R2, right? R2 had a dimension of 2 as well. Every basis for R2 had 2 vectors in it. So we could also say that the range of t is R2, all of R2. Right, so every vector in R2 is going to be an output. So in this example, the range of t is actually equal to the codomain. But still I write the is a subset, because it could be equal, but very often will be the case it won't be, so it'll be a proper subset like in the last example. but just keep this in mind, right? Do not say that they're all, here they're equal, right? Here the range of t is equal to the codomain, but that does not always happen, all right? That does not, as you saw with the last example, right? The range of a transformation is not always the codomain of that transformation. So again, I say at the bottom here, something to keep in mind, make sure you know this for certain. The range of a transformation is a subset of the codomain of that transformation. Right? Might be equal, but sometimes not. All right. Wonderful. So lots of terminology there, right? What is a transformation? Domain, codomain. What's the image of an input, right? The image of an input is simply its output. And what's the pre-image of an output? Now that's a little more complicated, right? The pre-image of an output was the set of all the inputs that had that output as an image. And then you had the range operator, right? Operator was a transformation where the domain and codomain were the same. And then you had the range, right? The range of a transformation is the set of all the outputs, right? All the values of the codomain that have a non-empty pre-image, if you want to think of it that way. Right? All the values of the codomain that actually have values that map to it, right? Or again, using terminology from this video, all the values of the codomain that have a non-empty pre-image make up the range of the transformation. All right, so lots of terms, lots of stuff to get in your head, and these terms will be used very often in the videos to come on transformations and linear transformations and matrix transformations. So please understand them. Hopefully get a grasp on them. Do plenty of examples where you're practicing using these terms. And again, get the hang of it so that future videos will be less confusing. All right, thank you very much for watching.